So in the previous two videos, we took on the somewhat monumental task of trying to go from the equation of a polynomial into the graph of that polynomial without using like graphing software like Desmos. And what we decided is we're not going to be able to do this exactly, but we can come up with an approximation of what the graph looks like. And that approximation will just include all the important characteristics of the graph. So in the last video, we learned that one of the important characteristics of a graph is what's called the end behavior. And the short story there is polynomial graphs do all sorts of crazy stuff in the middle, loosely speaking, of your graph, but eventually they settle down and either go up forever or down forever when we go far enough out to the right and far enough out to the left. And end behavior just describes that, whether it goes up or down when it goes to the left and when it goes to the right. And we learned how to write that mathematically, and then we learned how to determine that by looking at the end behavior of some monomials, and then finally learning that the end behavior of a polynomial is the exact same as the end behavior of the monomial that comes from the term with the largest degree. And if that doesn't make sense, we'll go back and watch the previous video when I go through that in like 10 minutes instead of like, 5 seconds. Unfortunately, end behavior isn't the only characteristic of these graphs that we want to make sure that we incorporate. In this video, we're going to learn about two more characteristics that we want to incorporate, and they're the intercepts. When I say the intercepts, all I'm referring to is where the graph crosses the x-axis and where it crosses the y-axis. Let's start with the low-hanging fruit, the y-intercept, where the graph crosses the y-axis. The y-axis is this vertical axis that you see pictured here in pink, and it turns out it's pretty easy to figure out the y-intercept. All you got to recognize is that if you're on the y-axis, you're not to the left, you're not to the right, you're right in the middle of the graph, and in the middle of the graph, the x-coordinate equals 0. So to figure out the y-intercept, all we have to do is figure out the output when the input, the x value, is equal to 0. And algebraically, that's super easy because when you have a polynomial, all of the terms have an x in them except for the constant term. So when I go putting in 0 in place of all of the x's, all of my terms are going to go away except for my constant term. So the output when the input is 0 is always just equal to the constant term. What I'm saying is this specific polynomial will cross this y-axis at 30 right here. Don't believe me? Let me pull up Desmos and look at what the graph actually looks like. Negative x cubed plus 10x squared minus 16x plus 30, an example that we've seen in the previous videos. We already learned its end behavior, namely that it goes up when we go to the left and it goes down when we go to the right. But now we want to focus on its y-intercept, and it looks like we crossed the y-axis right here. It's kind of hard to tell based on the scale of this graph, but maybe you'll trust me when I say this goes through the point 0, 30. In other words, the y-intercept is 30. And maybe you're like, all right, cool, intercepts are way better than end behavior where I had all these different cases to consider. Well, I'd counter that y-intercepts are way better than end behavior, but x-intercepts, where we cross the x-axis, is actually really complicated. Let me try to demonstrate that with this example. We got y equals x to the fourth plus 4x cubed plus 3x squared minus 4x minus 4. Just by looking at this thing, it would be nice if you could identify that the y-intercept is at -4 for this -4 right here, the constant term. And also it would be cool if you could look at this and recognize that the leading term is +1 times x to the fourth power. So my end behavior is that as x goes to the left, in other words, tends towards -infinity, y goes up. And as x goes to the right, in other words, tends towards +infinity, y also goes up. The end behavior and the y-intercepts are very doable. What about the x-intercepts? Not so much. Why are these so hard? Well, to figure out the x-intercepts, we have to figure out when we cross the x-axis. And the defining characteristic of the x-axis is its height is 0. So really what we have to figure out are all of the x values, all of the inputs into this machine that would make the output 0. To figure out the x-intercepts, really we need to solve x to the fourth plus 4x cubed plus 3x squared minus 4x minus 4 equals 0. And you do not know any ways to solve fourth degree polynomials like this. Second degree polynomials, sure, we got methods. We can factor or use the quadratic formula. But fourth degree polynomials, I'm betting you don't know how to do it. And you're never going to learn how to do it. And so you're like, wait, how am I ever going to find the x-intercepts? Well, let's change the question around a little bit. Pretend that instead of my function being x to the fourth plus 4x cubed plus 3x squared minus 4x minus 4, the function were x minus 1 times x plus 1 times x plus 2 squared. Just pretend that that was the question for a minute here. And yes, I recognize that this might not look like a polynomial the way we define polynomials, but just grant me this, pretend this was your machine, and you're trying to figure out the inputs that would make the output equal to 0. In other words, pretend you were trying to solve x minus 1 times x plus 1 times x plus 2 squared equals 0. We already agreed that this we don't know how to solve, but this would be pretty easy, right? Because it's a product of these different factors, the only way you can multiply together things and get 0 as the answer if one of those things themselves are 0. So either x minus 1 equals 0, or x plus 1 equals 0, or x plus 2 squared equals 0. I can solve these three equations, add 1 to both sides here and get x equals 1, subtract 1 from both sides here, get x equals negative 1, take the square root of both sides here and get x plus 2 equals 0, which I can then solve to get x equals negative 2. And I get the solutions to this equation right here. What I'm saying is if this was the polynomial that I was interested in, well then its x-intercepts would be really easy to find. There'd be one at positive 1, one at negative 1, and one at negative 2. And you're like, right, but it's not. And I'd counter with, actually, it is. This polynomial and this polynomial are identical. Okay, to be fair, we don't yet know how to go from this form to this form. That's what we're going to learn in the next section. But I can show you that these two are identical by starting with this form and showing how it's equal to this form. I can take this factored form and expand the binomials to show that that's equal to the unfactored form. This isn't something that you need to know how to do, but let me show you anyways. If I take the x minus 1 and the x plus 1 and multiply those together, the x times x gives me x squared, the x times the 1 gives me 1x, but the negative 1 times the x gives me negative 1x, so those cancel out, and the negative 1 and the 1 gives me minus 1. And then if I think about x plus 2 squared, this is really x plus 2 times x plus 2, so if I FOILed that all out, I'd get x squared plus 4x plus 4. The product of these two polynomials, I have to make sure that each of these two terms get multiplied by each of these three terms. So maybe I would first take the x squared and multiply it by all three of these terms. That would give me x to the 4th plus 4x cubed plus 4x squared. And then take the negative 1 and multiply it by each of these three terms. And that would give me negative x squared minus 4x minus 4. If I combine like terms here, I got x to the 4th plus 4x cubed, and then I got positive 4 of these x squareds minus 1 of these x squareds. So I have 3 of these x squareds minus 4x minus 4. And sure enough, what I've produced here is identical to what we started out with up here. This factored form and this unfactored form are equivalent. So what we'll end up doing is learning how to go from the blue form to the green form, because if we have the green form, then we can come up with the x-intercepts pretty easily. And the good news is right now you don't have to worry about it. This red line right here, how do you go from the unfactored form to the factored form, is a problem for the next section, the next two sections actually. In this form, just pretend I start you out right here. X minus 1 times x plus 1 times x plus 2 squared. Maybe you'd recognize that this is equal to some polynomial. If you want to spend the time to expand it, you can find out what that polynomial actually is, but you don't need to. And the x-intercepts of that polynomial are pretty easy to come by. I get a positive 1 from this factor, a negative 1 from this factor, and a negative 2 from this factor. Let's see, x equals positive 1 right here, x equals negative 1 right here, and x equals negative 2 right here. I already knew that the y-intercept was at negative 4, so that's somewhere down here. And from the end behavior, I know that when we go to the left, the graph goes up. So maybe this arrow can indicate that end behavior. And when we go to the right, the graph also goes up. So here's an arrow that can indicate that end behavior. You can kind of see the outline of a graph coming together here. In fact, what's pictured in green here captures most of the important characteristics that we're concerned about. Really, all we need to do to finish up our graph is learn how are we going to connect these different dots to the two arrows that we have on either side. And in order to be able to do that, there's a few more vocabulary words that it'll benefit you to understand. So let me get those out of the way. The first one is this word roots. And you don't have to worry too much about roots. For our purposes, it means the exact same thing as x-intercepts. In other contexts and in more advanced classes, there's a slight differentiation between the two. But for our purposes, all a root is an x-intercept. But often, rather than refer to it as an x-intercept, we'll refer to it as a root. So I could say the roots of this polynomial are at 1, -1, and -2, exactly where my x-intercepts are. FYI, the roots are also referred to as the zeros of a polynomial. The second thing I'd like you comfortable with is what's called the fundamental theorem of algebra. And loosely speaking, all it says is where these roots come from are factors in this factored form. So I have factors of x minus 1, x plus 1, and x plus 2, and each of those different factors produce a root, namely 1, -1, and -2. All the fundamental theorem of algebra says, at least for the purposes of our class, is that roots correspond with factors. If you go back up to these factors, you might notice that this factor is raised up to the first power, this factor is raised up to the first power, but this factor is raised up to the second power. We want to be able to incorporate the fact that this factor is raised up to a power greater than 1. The way you incorporate that is by talking about the multiplicity of a root. All the multiplicity of a root is the power that that factor is raised up to. So to use all three of these words, roots, the fundamental theorem of algebra, and multiplicity, kind of all together, what I would say is, in the factored form, this polynomial is x minus 1 times x plus 1 times x plus 2 squared. That yields the roots at 1, -1, and -2, and the root at -2 has a multiplicity of 2, whereas the roots at 1 and -1 have multiplicities of 1. Sometimes when you're listing the x-intercepts, it's worth pointing out the multiplicities. This multiplicity is 2, this multiplicity is 1, and this multiplicity is 1. Not because of the 1s and the 2s that you see in here, but because the implied 1s and the 2 that you see right here. The last comment that I want to make is the sum of the multiplicities, this 1 plus this 1 plus 2, is 4. And you might notice that the degree of this polynomial is 4. And that's not a coincidence. When our polynomial factors into linear terms, like they always will in our class, the sum of the multiplicities of the roots is the same as the degree of the polynomial. What does that mean? It means that if I have a fourth degree polynomial, the sum of the multiplicities of the roots must be equal to 4. So if the multiplicities were all equal to 1, I would have 4 different x-intercepts. In other words, a fourth degree polynomial can have at most 4 roots. Often, instead of saying that a fourth degree polynomial can have at most 4 roots, we say that a fourth degree polynomial can change directions at most 3 times. When I say change directions, I just mean change from going down to going up, or going up to going down, or going down to going up. The maximum amount of turns is always 1 less than the maximum amount of roots, because if you have just a single turn, like I do here, you can produce 2 different roots. And you're like, all right, cool, now I can speak really complicated using all this deep mathematical lingo, but how does that help me connect the dots? Well, it turns out the way you connect the dots is just based on the multiplicity of the roots. If the multiplicity of the root is even, the graph, loosely speaking, bounces at that root. And if the multiplicity is odd, the graph goes through the x-axis. What am I talking about? Let's go back up here. Remember that this root at -2, the one that's pictured right here, had multiplicity of 2. What that means is that when my graph gets to this point, it's going to bounce off the axis. So it's going to turn around right there. The next important characteristic of this graph is it's going to go through this point. So at some point, it turns back around and starts heading down. I don't know what that point is, but I'm not going to worry about that. That's something we'll learn in a Calc 1 class. And then it passes through this root. Note that I didn't bounce off the graph at this point because this root at -1 has a multiplicity of 1. So since this 1 is an odd number, my graph goes right through at this point. Again, somewhere I'm going to turn around so that I can hit my next important characteristic, this y-intercept at -4. I don't know whether the graph turns around before I hit the y-intercept or if the graph turns around after I hit the y-intercept. It doesn't matter which one I depict because I can't learn where the graph turns around until I take a calculus class. But what I do know is that the next important thing that'll happen is it'll go through the axis at this point 1. Again, not bouncing off, but instead going through because the multiplicity of that root is an odd number. Note that that leaves me up on the correct side of my graph for me to have the end behavior that I'm supposed to have. I come up with this approximate sketch of the graph of x to the 4th plus 4x cubed plus 3x squared minus 4x minus 4 if I know that in its factored form, it's equal to x minus 1 times x plus 1 times x plus 2 squared. And you're like, oh, cool. Okay, so this is what the graph looks like? Not really. I mean, this graph captures most of the important characteristics, but the actual graph looks like this. Note that our end behavior is correct. It goes up when we go to the left and it goes up when we go to the right. Our y-intercept is correct. It crosses the y-axis at -4, just like we depicted here. Our x-intercepts are all correct, -2, -1, and +1. And the behavior at those x-intercepts is also correct. We bounce off at -2, whereas we go through at -1 and we go through at +1. The graph actually turns directions somewhere over here at like -1.5 with the y value of less than 1, which is not at all what I depicted here. But that's okay. Our graph is just approximate, it's not exact. Another thing that's wrong with our graph is it looks like this graph doesn't turn around, stop going down and start going up until after it goes through the y-axis. But again, we're not concerning ourselves with the points that the graph changes direction at. That's all stuff for calculus. This is not meant to be an exact representation of the graph. It's just an approximation that correctly captures the end behavior, the y-intercept, the x-intercepts, and the multiplicity of those roots. That's a lot of information. Let's see if we can take it from the start to the end with several different examples. Here's a perfectly good polynomial. It's written in its factored form. This will make it really useful for me to figure out its x-intercepts. You might be able to just look at this and tell that we have x-intercepts at +3 for this factor of x minus 3, -1 for this factor of x plus 1, and -2 for this factor of x plus 2. And while we're here, we might as well make note of the corresponding multiplicities. This root of 3 corresponded with this factor of x minus 3, and this x minus 3 is raised up to the first power, so the multiplicity of the root at 3 is just 1. The multiplicity of the root at -1 from this factor is this 2. Its multiplicity is 2. And the multiplicity of the root at -2 is +3. And here you might object. You might be like, wait a minute, you didn't give me the unfactored form, you just gave me the factored form. So how am I going to figure out the y-intercept and the end behavior? Well, the trick is you need the unfactored form, right? The y-intercept came from this -4 and the end behavior came from this x to the 4th. But we don't need all of the unfactored form. We never use this 4x cubed or this 3x squared or this -4x. We just need to find this -4 and this x to the 4th. And we can find that by doing something similar to what I did here, but a lot easier. Just sort of think about what would happen if you did expand all these different terms. If I were to multiply x plus 1 times x plus 1, the f in FOIL would give me an x squared, and then I'd get some other junk that I'm not concerned with, and then the L in FOIL would give me 1 times 1, or 1 squared. Similarly, if I took x plus 2 times x plus 2 times x plus 2, I'd end up with x to the 3rd power, a whole bunch of other junk that I'm not concerned with, and a +8. If I just want the leading term of my polynomial, I can take this x to the 1st power, and this x to the 2nd power, and this x to the 3rd power to get x to the 6th power, with a 1 as the leading coefficient. Then I'm going to get a bunch of other stuff that would be really hard to figure out, but I don't need to know what any of that other stuff is until I think about my constant term. My constant term will come from the product of -3 to the 1st power, 1 to the 2nd power, and 2 to the 3rd power. 2 to the 3rd power is 8. 1 squared is 1. 8 times 1 is just 8. -3 to the 1st power is -3. And the +8 times the -3 gives me -24. This -24 is just -3 to the 1st times 1 squared times 2 cubed. We don't need the entire unfactored form. We just need part of the unfactored form. Because with this unfactored form, I can tell that the y-intercept is at -24, and my end behavior can be described with this mathematical sentence as x heads towards -infinity, y heads towards +infinity, and when x heads towards +infinity, y heads towards +infinity. It goes up to the left and up to the right because this is even and the leading coefficient is positive. Can we put all of that into a graph? Sure. The y-intercept is -24. Okay, that doesn't really fit on my graph, but that's somewhere down here. I got to make sure I go through that point. What about the x-intercepts? Those were at +3, -1, and -2. and it might make your life easier if you indicate the corresponding multiplicities of 1, 2, and 3 respectively. What about the end behavior? We want to go up when we go to the right because of this second sentence, and we want to go up when we go to the left because of this first sentence. Now all I got to do is connect the dots. One more piece of information that I haven't told you when you're connecting the dots. We know that if we have odd multiplicity, the graph has to go through the axis. And if we have even multiplicity, the graph has to bounce off the axis. But you can actually be a little bit more precise than that. If the multiplicity is odd, the graph goes through the x-axis. And if that odd number is greater than 1, it flattens out as it passes through the axis. What am I talking about? Easier to show you with the picture. This multiplicity is 3 right here. It's an odd number, so I want to cross through the axis, but I don't just want to go straight through the axis like I depicted here where my multiplicities were 1. I instead want the graph to kind of flatten out as it passes through and then pass through. It's a minor detail and it's not super important that you incorporate it, but I figure I might as well tell you. Then there's some point in between these two, I don't know where it is, so I can draw it wherever I want, where the graph changes direction. I'll learn that point in a calculus class. The next important characteristic is this x-intercept at -1. Because the multiplicity is even, we're going to bounce off right there. The graph's going to then head all the way down. The next thing that happens is it crosses through the y-axis at -24, as I depict here. And then the last thing to happen is to pass through my final x-intercept. Because this multiplicity is just 1, it's going to go straight through the graph right there, connect up with this arrow, and I've got my approximate graph. There's a couple special cases that I have to go over, but if this example makes sense to you, I think you're picking up everything that you need for this pretty hard section. We can get the x-intercepts from the factored form. We can get the multiplicities of those different roots from the factored form. We can get the y-intercept and the end behavior if we kind of expand the factored form to come up with the first and last terms of the unfactored form. Incorporate all that information into an approximate graph. Don't worry about where your graph changes directions. Know that you'll learn those points in a calculus class. Connect the dots appropriately and you're done. Let's do a couple more examples. Here's one that might look a little bit different because our first factor is just x squared as opposed to x minus 4 or x minus 1. The easy solution here is to think about that x as x minus 0 because x minus 0 is the same as x. But by writing it in this form, it makes it a little bit easier for you to see all the information that we need to extract. The first thing we want are all the different roots or x-intercepts. Let's see, I have a root at 0 for this factor, 4 for this factor, 1 for this factor, and -3 for this factor. What are the multiplicities of those roots? They're 2, 1, 2, and 3 respectively. Eventually, when I draw this thing, I want it to pass through the x-axis at 0, +4, +1, and -3. What about the end behavior and the y-intercept? Well, to figure those out, I need to get an idea of what the unfactored form looks like. To figure out the unfactored form, the leading term is just the product of the x's raised up to their respective powers. So x squared times x to the first times x to the second times x to the third. If we add up all those different exponents, 2 + 1 + 2 + 3 gives us 8. So the unfactored form would start out with y equals 1x to the 8th power. Then there'd be all sorts of stuff that would be hard to figure out. And then we come across our constant term. For our constant term, we want 3 cubed times -1 squared times -4 to the first power times 0 squared. Wait a minute, 0 squared is just 0, right? And 0 times anything is 0? Yup. So wouldn't my constant term just be a 0? Yep, absolutely. So my y-intercept is just 0. In other words, I'm going to cross this y-axis at 0 right here. Oh, right, I already knew I was crossing the axis right there because it was one of the x-intercepts. My y-intercept and my x-intercept are the same point at the origin here. What about the end behavior? Well, that all comes from this term right here. Because this is even and my leading coefficient is positive, it goes up when it goes to the left, and it goes up when it goes to the right. So I got an arrow over here in this direction and another arrow over here in this direction. Connect the dots. I like to work from left to right, so I kind of start out over here. My first important characteristic is this -3, this root. This root at -3 has a multiplicity of 3. Because it's odd, I'm going to cross through the axis. Because it's greater than 1, I'm going to flatten out as I cross through the axis. So it's going to kind of look like this. The next point of interest is this point, which is both the y-intercept and an x-intercept. So at some point I want to turn my graph around. I'm not concerned with where it turns around. This root has a multiplicity of 2, so at this point I want to bounce off the graph and stay below the x-axis. The next point of interest is this x-intercept at 1. This root has a multiplicity of 2, so what's going to happen is it's going to bounce off that point also. And then the final thing that's going to happen in my graph is this x-intercept of 4. This x-intercept of 4 has a multiplicity of 1. So what that means is my graph is going to cross through the x-axis because this multiplicity is odd. And because it's only equal to 1, it's not going to flatten out as it crosses through. So it's going to look more like this. Fudge things a little bit so that I hit up with my arrow. And I've got an approximate graph of this polynomial. 2 more examples and then we'll call this video good. I know it's kind of long, but there's a lot of info in here. What if the factored form had a negative 3x, for example, out in front, as opposed to this x squared that you see right here? How do you solve that problem? Well, I think the easiest way to think about it is we would have negative 3 times x minus 0 times x minus 4 times x minus 1 squared times x plus 3 cubed. I'm going to need part of the unfactored form. So to first figure out the leading coefficient, I got x to the first, I got x to the first, x to the second, and x to the third. So I got x to the 7th power. But that x to the 7th power gets multiplied by this negative 3. So I get negative 3 times x to the 7th power. Then I get a bunch of stuff. I'm not concerned with what it is. And then I figure out my constant term. My constant term is 3 cubed times negative 1 squared times negative 4 times 0 times negative 3. But wait, 0 times anything is 0, so it's just going to be a 0 like we saw in the previous example. This 0 right here tells me the y-intercept is at 0, which I could have figured out when I went to figure out the x-intercepts and looked at each of these different factors. This doesn't have an x, so it does not produce a root. The roots only come from the factors that have x's in them. So this factor produces a root at 0. This factor produces a root at 4. This factor produces a root at 1. And this factor produces a root at negative 3. The multiplicities of those different roots are 1, 1, 2, and 3 respectively. The only other thing that I need to consider is the end behavior. I got negative 3x to the 7 as my leading term. So what that tells me is that when I go to the left, this graph goes up. And when I go to the right, this graph goes down. If you have a hard time coming up with those two, review the video on end behavior, and specifically this monomial here, where the leading coefficient is a negative number and the exponent is an odd number. If you have this picture in mind here, it's pretty easy to come up with this end behavior. Namely that when we go to the left, we go up, and when we go to the right, we go down. My y-intercept we already saw was at 0. My x-intercepts are at 0, 4, 1, and negative 3. And I'm going to make note of their corresponding multiplicities because that'll make it easier to graph this thing. My multiplicity for the root at 1 is 2. My multiplicity for the root at 4 is 1. Now I connect the dots. The first important characteristic is this x-intercept at negative 3. Because the multiplicity is odd, I want to pass through the graph. Because it's greater than 1, I want to flatten out as I pass through the graph. At some point, I don't know where the graph is going to turn around. And then I hit this y-intercept and x-intercept at 0. Because the multiplicity is 1, my graph just passes completely through. At some point, I turn around. My next important characteristic is this x-intercept. Because the multiplicity is even, I bounce off. I turn around one last time to pass through this x-intercept at 4. The multiplicity is just 1, so I go right through and end up with my end behavior pointing down when I go to the right. One last example and then we're done. I don't know if we even need to do this example, but I wrote it down and this stuff's hard and repetition is a good thing. So let me show you how I would think about this one. First, we want the unfactored form. So this x to the 3rd power times this x to the 2nd power gives us x to the 5th power, but that needs to get multiplied by this 2. So I got 2x to the 5th. I got a bunch of stuff I'm not going to concern myself with. And then the constant term would be negative 1 squared, which is positive 1, times negative 3 cubed, which is negative 27, times 2. So 2 times negative 27 times 1 is negative 54. That constant term of negative 54 is going to tell me my y-intercept. This 2x to the 5th is going to tell me that when I go to the left, my graph goes up, and when I go to the right, my graph also goes up. What about the x-intercepts? I can get that from the factored form. The factors that have x's in them lead to an x-intercept. This factor of x minus 3 gives me an x-intercept of 3. This factor of x minus 1 gives me an x-intercept of 1. The multiplicities for those roots are 3 and 2 respectively for this 3 and this 2. That's all the information we need to extract. All that's left to do now is draw the graph. We got x-intercepts at positive 3 with a multiplicity of 3 and positive 1 with a multiplicity of 2. We got a y-intercept of negative 54, which is not going to fit on my graph, but it's somewhere way down here. To figure out the end behavior, we can just focus on this term because the leading coefficient is positive. That means when I go to the right, it's going to go up. And because the degree of this term is odd, that means it's going to go in the opposite direction when I go to the left as when I go to the right. So when it goes to the left, it's going to go down. When I go to the right, it's going to go up. Mathematically, I can write that as x approaches negative infinity, y approaches negative infinity, and as x approaches positive infinity, y approaches positive infinity. What about the x-intercepts? Well, each of these factors that has an x in it leads to a root, in other words, an x-intercept. This factor of x minus 3 gives me an x-intercept at 3. This factor of x minus 1 gives me an x-intercept of 1. The multiplicities of those roots are 3 and 2 respectively for this 3 and this 2. So if I wanted to keep track of my multiplicities right below my x-intercepts, I could write it like that. I got all the information that I need. I can graph this thing. The y-intercept is at negative 54, which unfortunately doesn't fit on my graph, but maybe you can kind of picture it somewhere way down here. The x-intercepts are at positive 3 and positive 1, so I can indicate those here and here. And then the corresponding multiplicities are 3 and 2 respectively, which I like to note on my graph just to make my life easier later on. What about the end behavior? When I go to the right, this thing goes up. When I go to the left, this thing goes down. All that's left to do is connect the dots. I kind of start down here. I pass through this y-intercept somehow. The first important characteristic is this x-intercept at 1. It's tempting to go through the x-axis here, but don't, because this is an even number. You want to bounce off the graph right here. At some point, I don't know where, my graph turns around, and then I have to pass through the graph at an x value of 3. However, since the multiplicity is greater than 1, I want to flatten out as I go through that point, connect it up with this arrow, and I'm done. I have the graph of this polynomial. I better end this video here because this got really long, but I think it was good that it was long. This is a topic that tends to give students a lot of trouble, and so it really helps to have repetition. What you want to be able to do is, if I give you the factored form of a polynomial, make sure you can come up with an approximate graph. And by approximate graph, what I mean is, make sure you have all the different x-intercepts, make sure you properly depict their multiplicity, make sure you got the y-intercept and the end behavior. And for those last two things, the y-intercept and the end behavior, what you probably want to do is come up with part of the unfactored form by thinking about how this would expand if you were to expand it, even though you're not going to actually expand it because that would take you forever.